In quantum mechanics, perhaps the most discussed or most asked topic is wave packet. And in this lecture, we have to discuss two aspects of wave packet. And first is that wave packet cannot extend from minus infinity to plus infinity. The reasons are related to that minus infinity plus infinity would make infinity, and that would make total probability also infinity. I have to tell you why. This is a just outline, but here I tell you that there's an argument for that probability density should be 1, so that means the wave probability density and wave function should not extend from minus infinity to plus infinity, and this requirement is called that wave function and probability density must be localized. So that's one aim to justify, to tell you details of what I've said. In a way I've said, but maybe it was too quick. So that's one thing. The other thing is that the mathematical requirements of achieving that aim, I mean, in here, the localization, is that you have to take a linear combination, you can say like a sum, of plane waves. And I have to tell you what plane wave means. And different plane waves are to be multiplied by different numbers, and these numbers they are called weightage. And the weightage is different for different waves, that means different for different wavelengths, or in mathematical terminology, the weightage is a function of wavelength. So it's a new function to be introduced. It's called Fourier transform, or in general wave packet, and that is the second wave function to be introduced in this course, in addition to the first wave function for which we started with the course, and that was position wave function. And that was a function of position, and this will be a function of wavelength. Different wavelengths have different Fourier transform. So this is another function to be introduced, and that is the target of this course, to introduce that another function. Now detail of that is, the first is I have to tell you what is plane wave. So plane wave is a wave that repeats with same wavelength everywhere. You have to just, it's a picture. Of course, no one can draw infinity. You have to use your imagination wherever infinity comes. Think of that. This space limitation has stopped me. Otherwise, I would have, the idea is to continue it everywhere. There's no preferred place. That's one thing. But if you take this formula, to get this graph, you can use trigonometric sign. But trigonometric sign has preferred place when this x is so that this angle is 90 degree. You have more square, and quantum mechanics square is probability density. You have more probability, more chances at some place of x, and the other place when it becomes 0, it's a less. So the different places have different probabilities. That is, there are some reasons. Some reason I can tell you in today's lecture, some later, that this is not an acceptable plane wave in quantum mechanics. Other subjects may use this plane wave, but quantum mechanics does not use. The reason is partially this, that this has different values of probability density of different values of x. Now, if for some reason or other you want to get a plane wave in such a way that it's same everywhere, then the mathematical is, the way is that, this graph can be achieved as a graph of sine. And the graph of cos, trigonometric cos, is also same, only shifted. But sine and cos, they are combined into e power iota. The rule that combines is called Euler formula. Now use that combination of sine and cos, which is Euler combination. You take exponential, and now you multiply this with this complex conjugate, and the answer is constant, which is same everywhere. So now if you ask, if you actually want to do full reason why I am preferring a plane wave which is same everywhere, so honestly, the actual reason is that this is a result of using that e power iota form, and e power iota form is a solution of a very much used equation of quantum mechanics that's called Schrodinger equation, which has a solution of e power iota, Schrodinger time dependent equation. But trigonometric sign is not a solution of Schrodinger time dependent equation. So that is the actual reason, but in quantum mechanics, but it is not possible for me to tell you this actual reason. For the moment, I've tried you to make it, if not justified, at least plausible that this form of plane wave is to be preferred over trigonometric one. And with that, we continue. Now, if you have that trigonometric, e power iota, it's multiplied with complex conjugate, probability density become constant, and the probability to get probability is, the way is to get area under this graph, and if it is constant, it's a horizontal line, and if height is finite, and the width is from minus infinity to plus infinity, total area is infinity multiplied with finite, that is infinity. But that is wrong. Probability must be 1. So what we have to do is, we have to make probability 1, then we have to think of a way around that it should not be same minus infinity to plus infinity same. There must be way to, the terminology is that must be way to localize it. The wave function must be localized. It should not extend from minus infinity to plus infinity as a finite value probability. Now the next question is how to get that localization, and that's the next portion of this lecture. And the portion here it is that we want is, if we want at infinity 0, if one plane wave is not 0 at infinity, there can be two plane waves and they can cancel each other. Where one is the maximum of that, the other can have a negative maximum, the total can be 0. It's just an idea. Actually, two plane waves do not do that. But for the moment, you just take it. Details are in next slides. That many plane waves combination may make at infinity a net 0. They can be positive, they can be negative. Net could be anything. Now, if the net at infinity is 0 here, minus infinity plus infinity, that is called localization. So next is how to get localization. Does this idea work? For that, first I show you a graph with two waves. Previously I had many waves, but if you have two waves, you take that and you multiply with complex conjugate, the result is real. You make a graph of that and you get that. There was no cancellation, there was no 0, but now you have a 0. But the question, so it's a partial success, but the question is that 0 at infinity, does that survive? And the answer is so far not, because infinity you have to only imagine it. No one can show you actually infinity. So I can help you imagine, that's it. So what I've done is, I have done, the limit is minus 10 to plus 10, and then I have limit minus 100 to plus 100, and then you have to only imagine what would happen if we go on increasing minus and plus side, and at least you can increase another limit and so on, and that would tell you that if it becomes 0, then it again becomes non-zero. So it's not no permanent kind of infinity, 0 at infinity. So that idea did not work totally well. So the next is, whose significance I have to tell you later, but for the moment just listen to the idea, that you introduce a weightage factor. All the waves, they are not multiplied with equal values. This is multiplied e power minus 32. Now e power minus 32 minus 18, they are result of this formula. When you put n is equal to 4, it's 16 multiplied by 2, that's 32. Then n is equal to 3, 9, square is 9, that is 18, and so. Apparently, the graph doesn't tell you anything new, but the reason of introducing that is that this thing can be further modified in this way, with this formula which was graphed in the previous slides. In that you had, and we have now in front of us still, n. N is discrete, and if you replace it with the continuous k, and summation you replace with the integration, and here in place of 2 you introduce another parameter a, this in this form a square by 4. All in all, you do integration rather than summation, and the result of integration is that e power minus x dependence is, k was, on k we have done integration, so that's finished. The answer is only x. So x dependence is this, e power minus x square. At infinity, e power minus infinity, 0, at both infinities. So that's, it's a localized, that's the, at infinity 0, so it's only in a limited region, so localization is achieved. Now for that I show you again this integration. Now if you are worried about where the integration, why the integration result is there, so I make one comment. This is a calculus question, not a physics question necessarily. So you may or may not be interested in that. So I think you will be interested in this calculus detail only if you are studying this as a course, but in that case you have a teacher helping you. Or if you are yourself teacher, then you may be interested in mathematical details. But I don't take time of others. So what I do is that I have written all the calculus details, and you have to pay attention. Those who prefer, they can pause this video and stop it and then read, and they pay attention to this color. If this thing, this red is equal to red, where for a few definitions you can guess, or maybe I have written or not. So if you know integration, so that's it. And so one is a Gaussian integral, and the other topic is completing the square, but I don't spend more time on it, and I go to what I think mostly everyone agrees here. Some agree, some are interested, some not interested, but what I think is of interest of everyone is that this integral which I solved is this special case of what is called Fourier transform. And the Fourier transform is a special case of what is called wave packet. In Fourier transform, this was made, a k square was made an arbitrary function, and now this has no time dependence. In wave packet, this you introduce a time dependence as well. So this time dependent, which is actually changing with time, moving function, that is called many plane waves. The word many is there because of decay, and plane wave are this, and the result is localized. I shown you. So this thing is called a wave packet, and that is the topic was announced topic. Now conclusions are that the quantum particle must be localized, and how to get localization is to sum, and sum with a weightage, and weightage means the different wave lengths are to be multiplied with different numbers. So this means the number is a function of wavelength, or k. K is 2 pi divided by wavelength. So now a byproduct of all this is that we have introduced another function, and eventually it will be used in the course as another wave function. Why I say another, I mean is the one wave function with which we started the course was position wave function. That is where the probability of detection is how much is at different positions, and now the probability of detection will be for different wavelengths. So that is another function. So that means what I said in the course initially, I discussed a possibility that position wave function and probability is full quantum mechanics, and that was actually a question, a possibility, but actually that is not the case. Complete quantum mechanics has other things as well, and an indication is that you have another wave function. So that's all for this lecture. And for implications of other wave function and uncertainty principles and de Broglie and phase velocity, group velocity, and all this which is related to that, you stay tuned. And the way to stay tuned is that you should subscribe to this channel, Clear Thinking. So I hope you will do that, and I will see you in the next lecture.